Hello, everyone. I am Sixun Huang from National Kaohsiung University of Science and Technology, Taiwan. Support vector machine, short for SVM, is a popular and widely used statistical model for classification. In this video, we will detail what SVM is and how it works. To simplify the explanation of SVM, we only discuss about the SVM in case of separable classes. The outline of this lecture includes introduction about the idea of SVM, maximum margin formulation about how to formulate the classification problem as the one that maximizes margin between two separable classes, dual representation about the further reformulation of the classification problem using Lagrange duality, hyperplane derivation about the way of how to derive the SVM hyperplane. SVM is originally a binary classifier by a decision function f of x. If f of x is greater than 0, the output label is +1. If f of x is less than 0, the output label is -1. For geometrical perspective, f of x equal to 0 can be considered as a hyperplane, where w and b are normal vector and the bias of hyperplane. For a two-dimensional example, the hyperplane for separating the two classes can be expressed in this form. The points in the light blue and the gray regions are with class labels +1 and -1 respectively. SVM is a kind of supervised machine learning. Machine learning means that SVM hyperplane is derived by a given training data set. Supervised means that all samples are well labeled. For a 2D example, we give a data set consisting of 3 samples for training SVM hyperplane. S denotes the feature vector, and the label of every sample is provided as well. Blue circles here denote -1 class. Green circle is +1 class. Based on the training data set, the hyperplane decided by SVM is the one that maximizes the margin around the separating hyperplane. Margin is the distance between the supported hyperplane formed by difficult points that are training samples closest to the hyperplane. For example, the red hyperplane is better than the purple hyperplane here, because it has a wider margin. These difficult points in yellow circles are called support vectors. Here give the detailed steps of how to determine the SVM hyperplane in this lecture. The first step is to introduce the maximum margin formulation, followed by introducing Lagrange multipliers for all training samples. Next, we reformulate the maximum margin problem in a quadratical programming problem for Lagrange multiplier solving. The obtained Lagrange multipliers are then used for computing the normal vector and the bias of the SVM hyperplane. After introducing the idea of SVM, we then give the formal formulation of SVM. For a training data set consisting of n training samples, and each training sample has its feature vectors and a label. For mathematical convenience, we assume that the two class labels are +1 and -1. Here, we give the example of training dataset D consisting of 3 two-dimensional training samples. The goal is thus to find the optimal hyperplane that has maximum margin. Without loss of generality, assume that the two support hyperplanes with maxima margin are W transpose times S plus B equal to plus 1 and minus 1. According to geometry theory, the distance between two parallel hyperplanes is the absolute of bias difference over norm of normal vector. That is 2 over W norm. Therefore, the parameters W and B hat of the optimal hyperplane is obtained by maximizing 2 over W norm. For mathematical convenience, it equals to minimize 1/2 times W norm square. The conditions that the optimal hyperplane must meet is that all training samples must be correctly classified. For all plus 1 training samples, they have to satisfy this equation. But for minus 1 training samples, they have to satisfy this equation. These two kinds of conditions can be put together as Ti times W transpose times Si plus B is greater or equal to plus 1. By moving 1 from right to left-hand side, we have the conditions for all training samples as these equations. In short, given a training dataset D, the goal is to find an optimal hyperplane that minimizes 1/2 times W norm square under these conditions for all training samples. For formulating the previous example of the training dataset D, the goal is to minimize this term. Since there are 3 samples, we have 3 conditionals to be satisfied. Each equation corresponds to 1 training sample. Here shows the equations in the other forms. In order to solve this optimization problem with inequality constraints, we have to introduce Lagrange multipliers and add the KKT conditions. KKT conditions for inequality conditions are stated as follows. If you want to minimize f of x subject to the inequality conditions g of x greater or equal to 0, it equals to optimize this Lagrange function L with Lagrange multiplier lambda and satisfy these 3 KKT conditions. Partial L partial S equal to 0. Lambda is greater or equal to 0. Lambda times g of x equal to 0. Since there are n inequality conditions in maxima margin formulation, we then introduce n Lagrange multipliers from lambda 1 to lambda n for each inequality conditions. Accordingly, we can obtain the Lagrange function L for maxima margin formulation as this equation. Here shows all KKT conditions for the Lagrange function L. The first 2 conditions are for the unknown variables W and B. The third ones are for Lagrange multipliers lambda 1, lambda 2 to lambda n. The last one are for inequality conditions for all training samples. Here shows the Lagrange function for the aforementioned example with 3 training samples. Lambda 1, lambda 2, and lambda 3 are the introduced Lagrange multipliers, each of which is for the inequality condition of a training sample. Here shows the KKT conditions for the Lagrange function of the given example. The first 2 conditions are for the unknown variables W and B. The third part is for the 3 Lagrange multipliers lambda 1, lambda 2, and lambda 3. The last part includes the 3 conditions each of which is for inequality condition of a training sample. Next, we want to eliminate W and B in Lagrangian function L by using these two conditions: partial L, partial B equal to 0, partial L, partial W equal to 0, so as to obtain the other formulation. According to fundamental theory of calculus, this term is 0 because it is not the function of the variable b. And this term becomes Ti because it has a variable b. Thus, partial L partial b becomes minus summation of lambda I Ti over I equal to 0. By multiplying minus 1 at both sides, we have a summation of lambda I Ti over I equal to 0. As for partial L partial W, this term becomes W, and this term becomes TISI. Thus, we have W minus summation of lambda I TISI over I equal to 0. Accordingly, we have W equal to summation of lambda I TIXI over I. Having these two equations in hand, we then substitute them into Lagrangian function L for variable elimination. Firstly, we multiply lambda I into each term in the right equation. Then we expand the summation operator and move the constant terms in front of it. This term is W, and this term is 0 according to the obtained two equations. Thus, Lagrangian function equal to 1/2 times W norm square minus W norm square plus the summation of lambda I over I. And this become the summation of lambda I over I minus 1/2 times W norm square. Since the W norm square is equal to W transpose times W, we have this equation. Then, substituting W by sum of lambda I TISI over I, we have the following equation. Then, by expanding sum operator, we have lambda 1 T1 S1 transpose plus lambda 2 T2 S2 transpose to lambda n Tn Sn transpose times lambda 1 T1 S1 plus lambda 2 T2 S2 to lambda n Tn Xn. After that, we distribute each term in the left equation to loss in the right equation, and finally have this equation. This Lagrange function is the quadratic function of Lagrange multiplier. So you can consider this equation as in the form of A times lambda square plus B lambda plus C, where A is less than 0. Accordingly, the problem of margin maximization equals to the one of maximizing this Lagrange function. And according to previous discuss, there are two conditions on lambda. The first one is lambda I is greater or equal to 0 for all I, and the sum of lambda I Ti over I is equal to 0. The Lagrange function of the previous example is shown here. The equation in rectangle is for sum of lambda I for all I, and in green rectangle is the sum of lambda I lambda j Ti Tj Xi transpose Sj over all I and j. After mathematical calculation, we have the Lagrange function as this equation. So the dual form of this example is to maximize this Lagrange function subject to the conditions that all lambda I are greater or equal to 0, and the sum of lambda I ti over I is 0. That is minus lambda 1 minus lambda 2 plus lambda 3 is 0. After introducing the dual form representation, we talk about how to derive the SVM hyperplane. The first step to derive SVM hyperplane is to solve the quadratic programming problem to find all Lagrange multipliers. Since quadratic programming is beyond the scope of this lecture, we consider it as a black box for finding Lagrange multipliers. Having Lagrange multipliers in hand, we can compute the normal vector of the SVM hyperplane as the sum of lambda I, ti, si over I. For example, if the Lagrange multipliers for these three samples are 2 over 5, 2 over 5, and 0 respectively. According to this equation, we have W equals to the vector 2 over 5 and 4 over 5. Remarkably, W is only determined by the samples with non-zero Lagrange multipliers. So we call these samples with non-zero Lagrange multipliers as supporter vectors. Finally, B can compute it using either negative or positive supporter vectors. For negative supporter vectors, it satisfies the equation W transpose xi plus b equal to minus 1. For positive supporter vector, this equation is equal to plus 1. By taking negative support vector 1, 1 as an example, we have the inner product of these two vectors plus b equal to minus 1. After simple mathematical calculation, we have b equal to minus 11 over 5. So the equation of SVM hyperplane is 2 over 5 times S1 plus 4 over 5 times S2 minus 11 over 5 equal to 0. In this lecture, we detail the idea of SVM, as well as the formulation and the derivation of SVM hyperplane. Thanks for your listening, and have a nice day.